How's
So
everybody doing today?
we have another 2 minutes to go, and we have our president now here. Alan,
Hey,
hello.
how you doing? I'm sorry I'm not there today. I had some car trouble last night, and so I'm stuck at home.
Oh, we were wondering where you were because I mean we were expecting that you're coming in late or something because you miscalculated how long it takes to get here, but
Well,
couldn't get in.
that was yeah, no, I looked at that also, and there was by the time I was able to get the car working and fixed, there was no way to actually get there in time because it was this morning before I got it out of the shop.
Wow, wow, that's pretty bad.
Yeah.
Uh, I guess we have everybody back. I mean, we have our speaker here, so I guess you don't have to start exactly at 3. We can start at 14:59. So I'm going ahead. So our first speaker for this afternoon session, for the second afternoon session, is Eileen Herwig from the Max Planck Institute for Astrophysics in Garching in Munich. So she has the longest distance to travel to us virtually. And Eileen will talk about the extended Lyman alpha emission around Redshift 3 quasar pair. So Eileen, take it away.
Yes, hi, can you hear me?
Yep, I think we can hear you just clear. That's
All
fine.
right, so thanks a lot for the invitation. As Dirk already announced, I will be talking about extended Lyman alpha emission. And what this essentially means is we are looking at the circumgalactic medium and the cold phase of it, so 10 to the 4 Kelvin gas. And to have a better understanding of what we're actually looking at, I want to start by showing you a cutout from a recent cosmological simulation of one host galaxy. And the dashed line you can see is the Vireo radius, and the galaxy itself you can see in blue. So it's called ISM gas, and everything in between is what we would call the circumgalactic medium. So this gives you like understanding of the scales. And the CGM is influenced by a lot of things like feedback mechanisms from the galaxy, but also cold accretion from the cosmic web. And this is roughly 10 to the 4 Kelvin. So this is what should be Lyman alpha bright. There have been multiple studies of this for single quasars at roughly redshift 3. So this is the largest one, but there are other ones. And you can see that all of them have basically emission. And when we look at it, the scales on which this emission is roughly 80 kiloparsec. And the Vireo radius of a halo like this at this redshift is about 100. So we really do see the CGM almost completely lit up in Lyman alpha, powered by those quasars. But when we there have been a few studies of multiple quasar nebulae, so those are examples for that, and those report much bigger extents. So for example, this is actually 4 quasars, and the nebula has an extent of about 300 kiloparsecs. So in theory, this should already reach into the IGM and not only show the CGM. So this motivated us to build a sample of physically associated quasar pairs. So we have a redshift cut and a angular cut at roughly redshift 3. And then we proposed for that at VLT Muse, and we got 8 of them observed with 45 minutes only per source. And what we get from Muse is a cube like that. And because we have high redshift, we have a lot of interlopers. So this is just a cutout from one of the cubes, but you can see there's a lot of things going on. I actually centered this on a point between the 2 quasars. So this is one quasar and this is the other quasar. And we have to remove, first of all the continuum sources, and we also have to remove the point stretch function from the quasar, because the quasar is very bright and we want to detect very dim emission from the CGM. And when we do that and then build a narrowband around the Lyman alpha of the nebula, this looks like this. So I still show you the position of the 2 quasars. The brighter quasar has a lighter blue, and I show you the 2 sigma and 5 sigma and 10 sigma, if possible, isotodes. And so this is the shape of the extended emission on CGM scales, if I remove all of those sources. Now this one is very dim, but we do find some very bright and very extended nebulae. So this is actually the brightest one, and this is very akin to those single quasar studies. But we also find very faint and small nebulae, which is not typical for those single quasar observations. We don't really see those. And we also see very peculiar morphologies. So then we, first of all, stacked all of that on top of each other. Sorry, this is a little bit of a busy plot, but in the background you can see other redshift 3 quasar surface brightness profiles. And in purple, you can see ours. And maybe you are able to tell that ours are dim in the center, but they are much more shallow. And if we fit a power law, we find a slope of 1.6 roughly, while normally people find -2, which makes sense because this is like the density. This is tracing the density distribution of the CGM, and there you would expect -2. So this might mean that in quasar pairs, the CGM density distribution is different. And then because we find those peculiar morphologies, we also wanted to analyze the morphologies. So here I show a different nebula to show it. In this one, we actually only have one quasar in the Muse field of view, and the other quasar is indicated by this arrow. And first of all, we determine the semi-major axis, and this is kind of the main direction of the nebula. And then I took the vector connecting the two quasars because I want to use this as a tracer of basically the large scale structure, because I would expect filaments between quasars, because I would expect them to sit in the nodes of the cosmic web. And then I calculated the angle between them to show how aligned the nebula is with the cosmic web, basically. And another metric I did is I measured the maximum distance between the quasar position and this 2 sigma isophote. And the reason why I do that instead of just doing the full extent of the 2 sigma isophote is because our nebulae are very asymmetric, and a lot of the times there's barely any emission on one side of the quasar, but a lot on the other. So this is a better metric of how far can the quasar actually reach. And when I plot this, what I find is that the angle and the distance are connected to each other, or like proportional, anti-proportional to each other. So if the nebula is very aligned with the cosmic web, it is bigger, and if it is not aligned, it is a very small nebula. Now, obviously, there are a lot of assumptions going into this, and there are also other caveats here. First of all, I checked if maybe the magnitude of the quasar makes a difference. So I color-coded the points by the magnitude. And I also checked if maybe the projected distance makes a difference. So the size of the dots is scaled by the projected distance. And we see this trend for both white pairs and close pairs. Here, white pairs are about 500 kiloparsec, close pairs are about 100. But there are still some issues with this. First of all, the very dim nebula I showed you in the beginning, this point around the brighter quasar is actually almost a circle. So getting a semi-major axis is very unconstrained. So this point is basically, it could be anywhere. Then we have this nebula, which I already showed you, which to me looks a lot like there's just gas stripping going on. So there's tidal interaction between the two galaxies, and ISM is being stripped, and boosting the density in the CGM and leading to this excess emission. And obviously tidal interaction will be aligned between the quasars. But we also have these quasars where the separation is so big that they really shouldn't be influenced by each other through tidal interaction, yet we still have this elongation in the direction of the other quasar. And so we think this is a genuine trend. Obviously, more data would be very helpful in judging this, but yeah. Another reason why we think this is a genuine trend is because it has been observed in simulations. So this is an example of a simulation where people tried to simulate Lyman alpha nebulae. On the left side, the number density of hydrogen. And this is a galaxy in the middle, again with the virial radius shown, and you can see the cold filaments. And on the right side, you can see the simulated Lyman alpha nebula of this same system. So this is actually oriented with the cold filaments. And there have been similar studies, but on very different scales, where people try to estimate the large-scale structure by basically getting a preferred direction of galaxies on megaparsec scales around quasars, and then looking at, again, the semi-major axis of the nebula. And there they also found a trend. So on the left side are all the detected galaxies on 30 co-moving particles, so very big. And on the right side, a nebula of about 300 co-moving kiloparsecs in extent, or like 400 probably. And the lines you can see, blue and yellow is the preferred direction of the galaxies, and pink is the preferred direction of the nebula. So this is also aligned. So that is why we think there might actually be a genuine effect here. So to summarize, in quasar pairs, the surface brightness profile is dim, but also more extended. And this also might be because our quasars are very dim, because there are just not enough quasar pairs to select from. Our nebula are often very asymmetric, and the biggest nebula are aligned with the large scale structure. So we believe those filaments influence emission on CGM scales. Yes, thank you.
Okay, thank you, Eileen. Questions for Eileen? Question? I have a question. Does the morphology, is the morphology affected by the distance of the two quasars when you look at the quasar pairs? Is there anything? Because I was thinking when I looked at some of the pictures that maybe, you rotate the two quasars around their center of mass, right? Is there something like that maybe involved?
Well, that is one of the things we wanted to investigate in this, is any trends with distance. And there's none. And this is probably just because Lyman alpha is a very complex line, because it's a resonant line, and there are a lot of effects like absorption by dust, etc., etc. So I think it's just too complex to have clear trends with a projected distance.
Yeah, and probably you need a larger sample, what you were saying at the end as well. Do we have any question online? I cannot see who is raising their, so you just have to unmute yourself and ask the question. Nope. Okay. Anything? Okay. Thank you, Eileen. Great that you could join us again. And and our next speaker is here. So the rest of the talks now, actually, the last much better. Let's try this entire screen. Let's try the entire screen again. Okay. Okay.
Okay, is it full screen?
Yeah,
Let's
okay,
go.
good. Now it's Alena
All
Spencer
right.
from Northern Kentucky. Sorry.
I got you. We're gonna hide that so you can see that one word that I put there. Okay. Oh no! Oh, spoilers. Okay. All right. Here's the title slide. Hi, I'm Elena. I work with Dr. Grupa. We're studying AGN, which Eric just talked about, but I'm doing an introduction to them, interestingly enough, and also talking about our research on this one. So we'll go ahead and move on.
Sorry, you have to build that sign.
No, it's fine. I can probably just stand here. That works. Yeah. So what is an AGN? That stands for active galactic nucleus, and that is a supermassive black hole at the center of a galaxy that's actively accreting material. So every galaxy does have a supermassive black hole at the center, but only about 10% of them are AGN, meaning they're actively accreting stuff. So the way we find these is basically if a galaxy's luminosity is higher than we expect to see for that galaxy. I'll talk a bit more about that later and how we really can tell this is brighter than expected. But yeah, this is powered by something called the accretion process, which emits a great amount of radiation. So there's the slide, spoiler slide. So these things basically exceed the luminosity of the host galaxy, meaning all the stars and everything in that, by factors of up to 1,000. So they are very bright. And here we have a cool gift, the accretion disk. So this is how the accretion process works. When material falls into the black hole by losing angular momentum, which you do have to do to fall in, otherwise it orbits at a constant radius, it basically accelerates and creates friction. So if you think about rubbing your hands together, that creates friction, heat energy, that's infrared. But the AGN does that on such a higher temperature scale that it emits in many different frequencies. So we get X-rays, UV, all of that fun stuff. The accretion disk reaches temperatures of about 100,000 Kelvin, which is quite a lot of Kelvin. So we also get emission lines from ionized gases, both in the vicinity of the black hole and farther away. So we get the broad line and narrow line regions. And that can help us tell a lot about the AGN from what we see there. This is just another slide on accretion here. So how do we tell if it's brighter than expected? Well, basically, this graph over here kind of shows us the region in the sky, the general size that we're seeing. And it shows that the flux doubles in, I think 2 light hours, if I remember correctly. So for that to happen, the region that we're looking at would have to be the size of our solar system. Unfortunately, or not unfortunately, just unexpectedly, the luminosity would be about 10 to the 40th watts here, and that would mean we need 10 to the power of 12 stars in that region, which is, not going to produce nuclear fusion. So that's how we know this isn't a fusion process, this is accretion, this is something else. So here's another fun fact, kind of. The accretion disk, interestingly enough, the temperature decreases when the mass of the black hole increases. So here, if we write the mass accretion ratio basically there, you can see the temperature is proportional to m to the negative 1/4, meaning the temperature is going to go down when the black hole gets more massive. And here is the anatomy of an AGN, so you can see kind of what we're looking at. You see the accretion disk is this flat part in here. It's flat like lots of things in our universe. There's angular momentum all spread out. The donut-looking thing around that is called the torus, and this is a region of dust, and it's obscuring some of the accretion disk. We have the broad line region labeled inside of there, and that is faster-moving gases that are very near the black hole. Now, these can be covered up by the torus, depending on your viewing angle, which I'll talk about in a second. We also have the narrow line region, which are gases farther away from the black hole, so they're less directly affected by what's happening inside of that. Both of these are ionized, and that's how we see the emission lines, basically. Yes, what do we have? So it's normal to see AGN vary just because the fuel supply is going to vary. The accretion activity can't be constant all the time. The food supply, as we call it, is not constant. So we do expect them to vary by factors of 3 to 5 within days. That's pretty normal. But we do get some with a lot stronger variability. So if you look at this diagram here, this line, being a logarithmic scale, this line is 1. So that means this AGN would not have changed the flux in this time period. And as you see, most of them are clustered around that line, including mine. That's where my source was. But we also have some that are much farther down, meaning they got a lot fainter or a lot brighter. And actually, Salem is going to be talking about that one next, so stay tuned for that. Dr. Gruba is talking about that one next, so how variable that is. It's crazy. So yes, we do see some with a much stronger variability. Now, what is up with that? Well, we can have about 3 different causes of variations. I'll just skim these because Salem's talking about them next. We have absorption, reflection, and changes in accretion rate. Absorption would be something like clouds in the sky. So if you think about the sun, I think it's cloudy out today, so the metaphor doesn't totally work. But if you have the sun and a cloud passes in front of it, it looks like it gets dimmer from our perspective. Now the sun didn't actually change its flux. Just from our perspective, something's blocking the radiation, so it looks dimmer to us. And the same thing can happen with AGN. So sometimes an absorber or some kind of gas in that region will cover part of the X-ray continuum, and we won't see that. So it just looks dimmer. We can also have a reprocessed emission from the corona, and this is essentially when the X-ray source, being the corona there, the photons both directly come at us and bounce off the accretion disk. So it looks like it's reprocessed and it looks brighter. This also causes the spectrum to appear harder or higher energy overall because of inverse Compton scattering. So we basically get something that looks like a harder spectrum from that. And finally, TDEs or accretion disk instabilities. Salem's talking about this, but essentially sometimes a lot more gas is added to our theoretical engine, and we get an increase in accretion rate temporarily. Some of them can come back around, and this can be periodic, but yeah. So how do we find out any of this stuff? So our work is mostly based on the SWIFT mission, which was a mission launched in November 2004, so it's like, what, it's almost 20 years old. Wow, almost 20. Happy birthday, not really, it's not November. But SWIFT has 3 different telescopes. This is one of its biggest benefits, is that you can observe in multiple regions at the same time. So we have the Burst Alert Telescope, which we don't use that much. We also use the XRT and UVOT as our primary methods. And SWIFT gives us shorter observations so we can have long-term monitoring campaigns. So we can kind of just check up on the AG and what it's doing, see if it warrants further investigation. So here is what's important for my source. Seyfert 1 versus Seyfert 2 galaxies. We have 2 main types of AGN, and if you remember, I talked about broadline and narrowline regions and the different emission lines coming from there. So the broadline regions are from faster moving gases that are very close to the black hole, and you can see that those are the emission lines there. And if you're seeing the broadline region, that is going to be a Seyfert 2 galaxy. If you're seeing only, I got confused. If you're seeing the broadline region, it's a Seyfert 1 galaxy. Can't read. Because you're looking at it basically from the inside. If you're looking at it directly on the edge, that's a Seyfert 2, and all of the broadline region is being blocked by the torus there. So that's how we tell that. So we also have a third type, and that is called a changing look AGN, which is basically when the type of emission lines we're seeing changes or the strength changes, meaning we might be seeing a different angle of the AGN over time. And that's what we are currently looking at. RxJ0128.1-1848, so catchy. So we detected this AGN, I believe, well, we detected it in the Rosat survey. But we had a few periodic observations from 2007 to 2015, and it was pretty high X-ray flux state, but then suddenly it dropped down drastically. And then XMM, another mission, was triggered to investigate that farther, because XMM takes longer observation times. We can see more data from that. Here is our most recent light curve. This does have all of the UV filters as well, but we're primarily looking at X-rays, which is at the top there. So as you can see, in about 2007 to 20, what is that, 19? No, I can't read, 17. It's pretty much steady in the upper flux state. But then in 2020, that data point is way far down there. So we basically triggered XMM in 2022, and then you see like the clustered observations, that's just more observations happening. And you can see it never really went back up to its initial state. But if you zoom in, it's kind of going up. Like if you look here, it's on an upward trend, at least from our last observation in February. But yeah, you can see the XMM observation there. Now, ultimately, that wasn't that interesting because it hasn't gone all the way back up to where it was before. But we did find something interesting about it. It changed the strength of its emission lines, which is characteristic of a changing look AGN. Kind of unexpected, because we were just looking at the flux variability. So here are the optical spectra with the emission lines. So for reference, if you see the O3 lines labeled on there, those are narrow line regions, so they don't really change based on what's happening around the black hole or what your viewing angle is. So as you can see, they stayed at about the same state between 1999 and 2023. But if you look at the H alpha and H beta lines, those being the broad lines, you can see they did change quite a bit. They did increase their strength. So yeah, that means something is happening, and it's not just all of the lines being changed, just the broad lines. So would probably indicate we're changing the viewing angle. We also have the X-ray spectra. So we have this one is a Swift 2008, so that's before all the drastic changes happened. And we also have XMM and New Star from 2023, New Star being in red. So we also use that observatory to see harder energies. So we get a more complete spectrum. What we found is that the spectrum did get harder overall. The normalization for the black body component versus the power law has changed. So we basically got the normalization for the black body component decreasing more than the power law. So that just means the energies, the ratio is harder overall. It's higher energy. So that is another thing we saw. And this is the most recent thing we worked on with this source. I'm still going through all the UV data. But to just look a little bit at the morphology, we decided to merge all of the UV data, which is about 45 kiloseconds, and we got a picture of it. So this is the W2 filter. So this being closer to visible wavelengths means we see the spiral arms better. And it's not the best image, but we do actually see the spiral arms a little bit. I just thought it was cool. Just a random side note, look at that galaxy. I don't know what that is, but it's somewhere in a catalog. All right, so what are we doing now? We are still analyzing all of the X-ray data from 2007 to 2024, and I'm also catching up on UV data, merging that. So we're still monitoring it with Swift, although it has been in SEM constraint since February, so we got our last observation then, and we'll pick back up when it's out of constraint. And yeah, thank you. That's basically what we're doing.
Questions for Alina? Kyle.
Sorry if this is a really good question, and it might be. Is it normal for AGN to change their orientation?
Orientation? No, it's not the
No.
orientation that changes now.
No.
Okay, I wouldn't think so.
No, it's not actually. That's why changing look is so interesting, and we don't know that many of them, right? That
Miriam.
Yeah, sorry. So this can be one reason for the changing look phenomenon, but isn't it also possible that obscuration is one? Okay.
Yeah, that's another option. Although a little bit surprising here is that your H beta line becomes stronger, right, when we see it in the low state.
Yeah, it was a lot stronger.
Right. So we don't know yet.
But yeah, these are pretty rare. That just that's what I was gonna.
Okay. Any other question? Do we have an online question? You guys need to speak up because I don't see it. I'm just taking down the slide and see if I can. Huh? Nothing? You see and nothing? Okay. Then I will close this. Thank you again, Alina.
Thank you.
And we go over to our next talk, which will be Selim Bolsing, who will talk about the story about IC 3599 and the calm before the storm, and talks about what's going on in this source. Can you see this on my screen? I haven't changed this yet.
Yes.
It's there, right?
Yes.
Okay. Selim, take it away. All yours.
Okay, my name is Salem. I work with Dr. Grupa, and this is the story of IC 3599. And IC 3599 is an AGN, and since Elena already talked about what an AGN is and how we observe them, I won't go over that. But she did already mention this, and I will go over it again. AGN are variable, and that's what we're interested in studying. All AGN typically vary by factors of 3 over any period of time, and this is considered to be normal behavior for them. However, we are interested in AGN that show high variability, which means they vary by factors of 10 or more. And IC3599 is an example of that, as listed on the graph. Where it's located shows that it's varying by factors of almost 100. So AGN are highly variable for 3 reasons, which are absorption, reflection, and change in accretion rate. So absorption is when an object such as a gas is in front of the AGN and its light becomes scattered, and this is similar to a cloud passing in front of the sun and the sky becoming dim. When this happens, soft X-ray photons emitted by the AGN will become absorbed by the gas, and hard X-ray photons will be able to penetrate through the gas. And when we detect the AGN, we are only able to detect the hard X-ray photons. Reflection is when a soft X-ray meets an AGN accretion disk and it interacts with its electrons. And that causes the soft X-ray to scatter to higher energies, and that soft X-ray becomes a hard X-ray. And when we detect this X-ray, the source appears to flare because of the increase in energy. Then the final cause for variability is change in accretion rate, and this can be due to accretion disk instability, such as a change in viscosity, and this is like fuel availability, as Elena mentioned. And there's also a tidal disruption event can be the cause of this, which I will explain later. And viscosity can change for 2 reasons, which can be an increase in temperature and an increase in pressure. And when this happens, the accretion disk becomes much brighter and the AGN appears to flare when it's detected. So IC3599 is the AGN I'm studying, and it's a Seyfert 1.9 galaxy that usually has a low luminosity. It's found in the outskirts of the Virgo cluster, which is about 92 megaparsecs away, and its mass is estimated to be 2 to 20 million solar masses. The image on the right is the deepest UV image of IC3599 ever, and it's in the W2 filter. The scale is, that bar is 4.4 kiloparsecs, which is huge, and its exposure time was 99 kiloseconds. So IC3599 first caught our attention in 1990. And you can see on the graph on the right, the x-axis is MJD, so it's just time, and then the y-axis is flux. And we can see by the 1990 label, there's a data point all the way up there, and that is why we became interested in it, and then soon after, it drops all the way down. So there was 2 theories to why this happened. There was a change in accretion rate, or it was caused by a tidal disruption event. So to figure out what was going on, an optical spectrum was taken, and in the optical spectrum, we saw strong hydrogen and helium lines, which are the main ingredients of a main sequence star, which is what led to the theory that this was a tidal disruption event in the first place. And so a tidal disruption event is when a star approaches a black hole and it gets ripped apart by its tidal forces. Some of the material of the star is accreted by the black hole, and the material of the star that's not consumed will either orbit the black hole or it will get shot outwards by gravity. IC3599 became interesting again in 2010, where it swooped all the way down and then went all the way back up. And this left us to wonder, why is it flaring again? And this is probably due to a change in accretion rate, but it does leave us to wonder if this is still due to a tidal disruption event. Those 2 images should have been switched.
Yeah, I don't know.
Okay, it was fixed before. I know that you know that this issue's happened before. Okay.
Yeah.
Okay, let me go back. This image right here.
This is the SED, yeah.
Okay, yeah. Let me talk about this image for this slide. Okay.
Uh-huh.
This image is basically this graph overlaid with the tidal disruption event model, which I will talk about soon. And this is basically the arcs is when it's predicted to flare according to the tidal disruption event model. And then a spectral energy distribution was taken while it was flaring in 2010. And the UV spectrum became blue, and I don't mean the blue data points, I mean an increase in frequency, which led to an increase in temperature. And this suggests that an entirely new tidal disruption event is very unlikely since they don't happen that often, especially not within 20 years. And this is probably due to a change in accretion rate. Okay, so the tidal disruption event is due to the Campana paper, and it assumed that the 1990 event was an original tidal disruption event, but afterwards that star was in a highly elliptical orbit, and it was only coming around once every 10 years. And each time it came around the AGN, it would be reaccreted, aka partially disrupted. And the Campana model predicted IC 3599 to flare again in 2019 or 2020. So now we're going to find out if it actually did end up flaring. So as you can see by the region bordered by the neon green, nothing happened, which disproves the tidal disruption event model, but does still leave us to wonder why IC 3599 is flaring in the first place. And this is still due to a change in accretion rate. So after a flare, the inner disk of the accretion disk empties, and the black hole will slowly build up its inner disk over time. Eventually, there's going to be more material in the inner disk than can actually be accreted by the black hole, and that extra material will cause an increase in gas pressure. This sets off a chain reaction where the increased gas pressure leads to an increased temperature, which decreases the viscosity and increases the accretion rate, which leads to a flare. And once this happens, then our disk gets empty again and the cycle repeats. So IC 3599 showed a little bit of interesting behavior in December of 2022 when it had a mini flare. The data points we want to focus on are the magenta. We can compare this with the 2010 flare, which the data points on the right, that's the X-ray portion of the frequency. They're all the way up there. The magenta data points are definitely below that, but they are definitely above the blue, which is its typical dim state. So it does leave us to wonder, why did it have this mini flare? And it's thought that this is due to a temporarily formed corona. And this is because we saw the spectrum get hard, and only the corona can produce that radiation. So what is IC 3599 doing currently? And it's been gradually recovering after its flare in 2010, and we can see its brightness gradually increasing since then. And we expect it to flare sometime in the 2030s. So a summary, the first flare in 1990 could have been either an accretion disk instability or a tidal disruption event. The second flare led to the tidal disruption event model, where a star was orbiting in a highly elliptical orbit and getting partially disrupted each time. And they predicted a flare in 2019 or 2020, but that never ended up happening, which disproved the tidal disruption event model and supports the accretion disk instability cause.
Okay. Thank you very much. All right. Questions for Salem? Okay.
I have a question.
Good. Yes, go ahead.
Yeah. So this is a very interesting object. Are there any others like it?
Not exactly like that. Not as far as I'm aware of. I mean, not that we know of. Well, actually, no, I should take it back. There's another one which is called NGC 3599, surprisingly. which we think is a tidal disruption event. The problem when you are dealing with these X-ray flares and you look at an AGN is you never know if this is a tidal disruption event or if this is an accretion disk event. You can never be sure because you have an accretion disk, which could be causing the flare. But in a non-active galaxy, the only way to get a flare like this is the tidal disruption event. So, Gary, just that's a good question. Anything else? Yes, Bennett.
If you have tidal disruption events, you can see those in the UV, you can see those in the X-ray.
Correct.
So you need something like an all-sky survey to find those?
Yeah.
Right, so this is kind of, would you, Rosette just completed theirs, or at least the.
You mean here?
Yeah, the German side.
Yes,
right?
yes, yeah.
So could you find tidal events there?
Yeah, you could.
Even in out to where is my next question. Like, so is this nearby galaxies or should you?
Nearby galaxies. Typically, I mean, every galaxy will have a tidal disruption event depending on their black hole mass, right? Because there is a Goldilocks zone. When you go too high, you can explain this, right? With the black hole mass, when the black hole mass becomes too large, what happens?
And what were you trying to explain?
I was trying to explain that if your black hole mass becomes too large, you won't get disrupted. Because what disrupts you is the tidal force between your feet and your head.
Distance. The distance is insignificant compared to how large the black hole is.
Yeah.
If it was a small one, then the distance would be significant and it would tear it to pieces. But with a large one, the force is not strong.
What's large and small? With black holes, I can never figure
Okay.
Like large would be like a supermassive black hole, like IC 3599.
That's not large. That's small.
Okay, never
Yeah.
mind.
Yes. Now,
Well, still
those are
bigger
the ones
than
that disrupt them, right? Because they are something like 10 to 6, 10 to 7 solar mass.
Yeah.
But at 10 to 8, you cannot disrupt anymore because your Schwarzschild radius is larger than your time disruption radius.
Oh, so you're.
So it's the same thing. If you want to dive into a black hole, you don't take a solar mass black hole with that because that will kill you. You want to jump into a 10 to 6, 10 to 7, 10 to 8 solar mass black hole, or even 10 to 9 solar mass black hole. You're good. The star is good. The star doesn't get disrupted. Because again, it's the difference between the feet and the head. Yeah.
My black hole is too large.
Yes. Yours is,
I tend to the 8, 10 to the 9.
yeah. You can jump into that. You will be fine. The stars will be fine.
At least for a little while.
Yeah, at least for a little while. Anyway, any other questions? Super, thank you. Okay, so quickly put the next one up. I hope you guys can see this in a second. The next one, the next speaker is, guess what, me. So I will talk about another galaxy that was already talked about, another active galactic nucleus presented on the poster, so pay attention to the poster as well, and also Elena pointed it out, WPVS 007. And WPVS 007 has nothing to do with James Bond. It was just the seventh object in a catalog, in an optical catalog by Baumstecker, Pietro, what was it? Vieto and Schuster or something like that. Older catalog from the 1980s. And so it was discovered during the Rosette Sky survey as one of the brightest AGN in the sky. It was the softest AGN in the sky. And so we got interested in this one. And the question was, what makes it so soft and what's going on? This is a narrowline Seyfert-1 galaxy. So Elena already talked about the different kinds, Seyfert-1 galaxies, Seyfert-2 galaxies. So what's a Seyfert, narrowline Seyfert-1 galaxy? Well, it's a Seyfert-1 galaxy. So it has broader lines in the permitted lines, so hydrogen, helium, and so on. But those lines are relatively narrow. And what causes the width of the lines? Well, you said this already, right? I mean, those are lines that are coming from the vicinity of the black hole. So we can use those lines to actually measure the black hole mass, because all you need two ingredients to measure a mass in the universe or anywhere is you need the velocity, you need the distance. So if the lines are narrow, that is already telling you that these objects are objects with small black hole masses. Now, when you look at the luminosity is at the same level as you see this at the big whopping high mass C1 galaxies, which also means that those guys have a relatively high accretion rate. So they are high L/L objects, and they are also what we consider young AGN. So they are AGNs, they are just at the first stage of the development. So when you are dealing with light, when you're dealing with a strong radiation field, you're also dealing with outflows. And Mariam was talking about this as well. You're looking at outflows that are coming towards you. Why is that? Because you deal with radiation pressure, right? And these are high L/L objects, so you will see strong outflows from them. Now, which are the objects in the universe where you can actually see the strongest outflows? Well, those are usually the broad absorption line quasars, which were discovered by the end of the 1960s. And guess what? They all had redshifts of 2. Why did they discover objects with redshifts of 2? Well, these are ultraviolet lines, right? When you shift them from a redshift of 2, well, they get into your optical regime that you can observe from the ground. So all these objects are high luminous AGN, high black hole mass AGN, and really whopping quasars. Those are really bright objects. So you can see these whopping outflows here. This is again what Miriam said earlier. So here's the carbon-4 line, for example, and you can see these troughs over here. And these outflows are blue shifted by about 10% or 5% to 10% of the speed of light. So there's a lot of mechanical energy put into these objects. On the other hand, we are dealing with objects like near-line C1 galaxies, because when you look at the broad absorption line quasars, those are high L/L objects. So it was then also suggested about 25 years ago already by Brandt and Sarah, so by Neil Brandt and Sarah Gallagher, that maybe there's a connection between near-line C1 galaxies and broad absorption line quasars, which then also was, Todd Borison was looking into this as well. So they are both high L/L, and the difference between them is basically the mass accretion rate that you're looking at. And the black hole mass at the end of the day, because the near-line C1 galaxies are on the low mass spectrum of the mass distribution of AGN, and the broad absorption line quasars are on the other hand. Now, how does this one get in? Now, again, WPVS 007 was discovered during the Rosat Sky Survey, like IC 3599. Again, it was one of the brightest AGN in the sky at the time. It was the softest AGN in the time. And then when we did some pointed observations a few years later, 2-3 years later, it dropped by a factor of 400. Now, the question was, of course, what's going on here? Why is a source that is so soft dropping so fast? And this is the Swift monitoring. I started Swift monitoring already back in 2005. So I've monitored this since 18 years, starting over here. We couldn't see it at first in X-rays because it's kind of, because it's a low it's a low luminosity source. I was not expecting it to see it, but at some point around 2010, we were actually able to pick up the source again with Swift. The question was still again, what's going on here? Now the answer came from a satellite called FUSE, that was the far ultraviolet FUSE Spectroscopy Explorer. Yeah, thank you. And that was an observation that was done by Karen Lely. I worked with Karen since about 25 years. So she started observing this WPVS 007 then in the ultraviolet. On the gray curve here, I hope you can see this also online, following here with the cursor, this is what you expect from a normal quasar, an unabsorbed quasar. The black spectrum here is WPVS 007. It is highly absorbed. And the cool thing is, this is a low luminosity, low black hole mass AGN. While from the prediction, what you expect is you see these absorption flows, these very strong absorption flows, only in high luminosity, high redshift, high black hole mass, active galactic nuclei, and we don't. Now, why is Swift so important for this source? Well, Swift can observe in X-rays as well in the ultraviolet and optical. So Swift does simultaneous observations in all these bands, and it allows us to get also colors. And We had also HST observations. So the black curve over here on the right side is an observation that was done by Bob Goodrich in the 1990s. And there were only narrow absorption lines, the ones that Miriam showed earlier from her AGN from Makarian 817. This is different. At first, we started out with only the narrow bands, but then we looked in 2010, and you see this whopping absorption trough here. This is what you see from a broad absorption line quasar. On the other hand, when you look at the UV data here, UVOT data here, this is the magnitude in the M2 filter, so at 2,200 angstrom, and then these are the colors. And you can see the source over here, it is bluish and it's bright. So you see a blue light and you see the absorption troughs. On the other hand, when we looked at other times, like look at 2015, the absorption troughs were very weak, only this almost disappeared. And in this motion, in this time, the source became red. It becomes dimmer, it becomes red, and your absorption lines are gone. Now, this is kind of mind-boggling, right? It's exactly the opposite what you expect, right? You would expect the source is dim, you see more absorption, you see stronger outflows, right? No, it's not, because what happens is, here's the little movie that I got from Karen. I hope this is working. So what we are looking at is actually, we are looking at a grazing angle over the torus. And the torus is not this donut shape, so it's not this solid body that you're looking at. It's actually kind of like clouds. It's some fluffy thing, right? So sometimes you look through areas where the source appears to be reddish because now you're looking through more material and you do not see the outflows because the outflows are blocked. When the source appears blue, like in this case here, you see the strong outflows out here. And that makes this source so interesting. The question is, of course, variability in the C carbon-4 line, or in these absorption troughs as well. That has been studied. Neil Brandt has a group that studied this. There was also, what was her name? Noor Felice Al, and she was looking in her PhD thesis with Neil into SDSX spectra of broad absorption line quasars. And some of them varied, but it was only the ones that had relatively low, not very strong absorption troughs, and not as strong as we see this in WPVS 007. So variability of broad absorption line troughs are known, but you only find them in a few percent of broad absorption line quasars, which is not per se very surprising, right? Because we are dealing here with objects with 10 to 9, even 10 to 10 solar masses. So everything in an AGN scales with mass, right? Because everything goes by the Schwarzschild radius, which scales directly with the mass of the central black hole. So that we find some is interesting. And the estimated lifetime of these things are relatively short, 170 years in these objects, when you go to the rest frame of these objects. WPVS 007 is much closer, low luminosity, low black hole mass, and we can study in WPVS 007 phenomena in broad absorption line quasars that we cannot really do in broad absorption line quasars, because the broad absorption line quasars, everything is so much slower going on than in WPVS 007. The other thing is, when you look at the variability of these, or the broad absorption line quasars that show this variability, their strength of the absorption line, so these are the ones with disappearing broad absorption line troughs, their equivalent width are relatively small. So look at this. This is, equivalent width in angstrom. Here's 10, here's 20, 30. And the ones that show the disappearing are over here, less than 10. When you look at WPVS 007, well, you look at 25. When it's low down here, it's about 10-ish or so, but it's significantly higher than you find in those broad absorption line quasars that actually absorb them, that actually show the variability. And what I want to point out is these data points over here. Again, we monitored since 2005 the source. I saw a couple of detections with Swift in 2010, 2011, up to 2012. And then over the last decade, absolutely nothing. So it was a big surprise when this thing emerged again in 2023, last year, in May and June. I had a bunch of observations with Swift on that time, was hoping that this thing actually becomes even a little bit brighter, because the red line here This is ROSA data over here. This is the SWIFT detections, and these are the SWIFT detections last year. The red line is my trigger for XMM. I have an XMM proposal which I can trigger for 25, 30 kiloseconds if this thing exceeds that threshold. It did not, so we have to still wait for this. So hopefully it comes back again at some point. It's basically the monitoring from last year, so you can see these are the detections. It goes down in the ultraviolet, so it becomes fainter and fainter. Fortunately, it's not as much affected. We talked at the poster about the SWIFT wobble as much as IC3599, for example, is, or any other nearby galaxy. This one is at a redshift of 0.03. The nucleus is bright enough that we don't see as much host galaxy contribution, so you can actually see that it goes down. We don't see this in IC3599. So what's the future here? The future is we continue monitoring. I reduced the monitoring from once every week to about every 2 weeks. And we are still looking for a high state, because if this happens, if I catch this source in a high state, I can actually trigger my pre-approved XMM observation for 25 kiloseconds. And the other thing is we want to look for some similar sources. So that's why we do also this monitoring of the 100 some sources I'm doing, because we want to find another Nearline C.1 galaxy that shows outflows. Right now, we don't. We don't have only one source that shows this, that shows the connection between the broad absorption and quasars and Nearline C.1 galaxies. That's it for me. Thank you very much. Any questions? Okay, yes.
So you talked about how like these in the secretion disk, especially after the outflow, there comes like different kind of sizes of clouds, kind of like there's space of like where it's like blue coming where there's not much clouds in there, and then there's clouds coming in. So these cloud sizes are like a little bit smaller in the accretion disk, right?
Correct. Yes. Yes.
Do you have like, is there things for scattering? Like, do you have how do you account for like the scattering that comes from these smaller clouds that come from the light beams? The smaller clouds?
We don't. We just take the observations as they come in, right? I mean, this is basically the interpretation that when you look at the torus. The torus is about a couple of light years away, maybe a parsec away.
Okay.
And then it rotates, right? Because it still rotates around the black hole, the central black hole.
So like whenever these cloud sizes are going about, is there kind of like uniform do you have like uniform pattern on
No, you don't. Not as far as I know. We don't see them. You're absolutely right? But right now, I wouldn't say so. Because otherwise you would see this. I mean, at least what we can do is we can follow a pattern with SWIFT, because we look at the colors. You would see the color change like a period, and we don't see this. It's more random. That's what I expect, generally speaking. Any other question? Any question online?
Yeah, I have a quick one. I'm trying to trace your DeSico reference. What is it again?
What one was that?
It was DeSico. It was about the BAL absorption profiles changing.
You mean? Oh, this one. Yes. Is that DeSico? Yeah, DeSico. Yeah.
I'm just trying to trace it. I couldn't find it.
I can send you a link later on, Gary.
Thanks.
Okay. Yeah, that's an interesting paper, because they take a bunch of SDSS spectra and look at them, compare them. Because SDSS has not been looked at one region for some time. It does this over multiple regions. All right. So I guess we go over to the next speaker, our last speaker for this session, which is Samia Mahmood from Bellarmine, and she will talk about properties of weak interacting from cosmic ray muons. And I will stop sharing here so you can actually. Hello.
Hello. Can anyone hear me?
Hopefully this works. You should be able to share your screen. If not, let me know. Then I have to change you and make you a co-host.
Okay. Can everyone see my screen?
Yes, it works. Great.
Wonderful. Okay. Go ahead and present. All right. Hello, everyone. My name is Samia Mahmood. I am a sophomore at Bellarmine University, and I work on this project with my mentor, Dr. Akhtar Mahmood. And today we're talking about determining the properties of the weak interaction using cosmic ray muons. So here we have the standard model with the 6 quarks and the 6 leptons. In the middle, we have the force carriers for the electromagnetic, the strong and the weak forces. And in the center, we have the Higgs boson, which of course is what gives mass to certain particles. And for this talk, we will of course be looking into the muon. So where do muons come from? Well, muons are a byproduct of cosmic rays, which are a stream of cosmic ray particles that are constantly entering the Earth's atmosphere. Primary cosmic rays, which are high energy particles, originate from outside the solar system from galactic events within the Milky Way galaxy. And this is called galactic cosmic rays. So this, of course, includes interstellar collisions of gases, protons ejected at extremely high energies from supernova explosions, and from neutron stars that enter the magnetic sphere and bounce around within the magnetic field. It is important to note that the exact mechanism by which these primary cosmic rays are accelerated is somewhat of a mystery. But what we do know is these high energy particles, which are produced from the explosion of type 2 supernovae, are accelerated in a galaxy through shock waves. And this, of course, can be visualized in these side images here. So cosmic ray particles have an energy range between 1 GeV to 1 billion TeV. By comparison, the highest energy that can be produced by an accelerator on Earth, like the LHC, is only 14 TeV. So it's clear that these particles can be very energetic. Additionally, it's important to note that the sun can also produce cosmic rays. However, these solar cosmic rays have low energies within the MeV range. Thus, they get deflected by the Earth's magnetic field and absorbed within the atmosphere. So primary cosmic rays are comprised of 99% nuclei, 1% electrons, and 0.1% positrons, out of which 89% are hydrogen nuclei, 10% are helium nuclei, and the remaining 1% are heavy nuclei, which of course are the end products of cell nucleosynthesis. So this includes carbon, oxygen, iron, and other nuclei which are synthesized in stars. Additionally, we have an image here which shows how the primary cosmic rays produce the secondary cosmic rays. So these primary cosmic rays, once they travel through the interstellar medium, they collide with the nuclei of atmospheric gas molecules, including nitrogen and oxygen, at around 30 kilometers above the surface of the Earth. So this will, of course, produce the secondary cosmic rays, which also include electromagnetic radiation. So once these primary cosmic rays enter the atmosphere, they ionize, forming matter and antimatter, such as the electrons and positrons, and protons and antiprotons. So for these secondary particles, these interact through the strong electromagnetic and weak force to produce a cascade of more particles. So among secondary particles are charged pions, which will then decay into a muon and antimuon neutrino through the weak force. Approximately 25% of the muons created in the upper atmosphere reach the Earth. And within cosmic ray showers, both muons and antimuons are produced. And these have a mean energy of about 6 GeV once they are approximately 15 kilometers above sea level. So now a little bit of history of cosmic rays. So here we have a picture of Victor Hess in his hot air balloon in 1912, where he observed penetrating radiation coming from outer space when he noticed an increase in the discharge rate of his electroscope. In 1925, Robert Millikan was the first to coin the term cosmic rays, and in 1929, Dmitry Skobelson was the first to build a cloud chamber to actually detect cosmic rays. The first muon was discovered in 1936 by Carl Anderson and Seth Nettermeyer, and a year later, Street and Stephenson confirmed the existence of muons using their cloud chamber. So how do we actually see muons, and how do they reach the ground? So given that muons can travel at about 99.9% the speed of light, and that they have a lifetime of 2.2 microseconds, the lifetime will actually increase by a factor of 22.4. Thus, the new lifetime is 50 microseconds. And this is due to Einstein's special theory of relativity through time dilation. And so it is important to note that the muons should have technically only decayed after only traveling 660 meters, given that they're produced at such a high altitude of 15 kilometers. But again, given time dilation and Einstein's special theory of relativity, the muon's lifetime will increase. Thus, they will age more slowly and can travel 15 kilometers down to the surface of the Earth. So here we have the decay path for cosmic ray particles. So here in blue, we have the protons, which are the primary cosmic rays. And these, of course, will produce pions, which are the secondary cosmic rays. And these pions will decay into muons. And the muons will then, of course, decay into an electron, an anti-electron neutrino, and a muon neutrino once they're inside of our detector. So these cascade of muons, which are referred to as muon flux, depends on the zenith angle. Thus, we are more likely to detect muons once they hit the surface of the Earth at 90 degrees. Additionally, the muon flux can vary anywhere between 0.4 to 1 muons per minute per centimeter squared. And of course, the muon flux also depends on the latitude. So for higher elevations, we expect the muon flux to increase. Here's a schematic of our setup. So we of course use a desktop cosmic ray muon detector, which contains scintillator pads, a photomultiplier tube, a high voltage power source, and this was connected to an external data acquisition module through a BNC cable. So the muon detector's data was fed to a laptop using USB cable, which ran the muon data acquisition software. And this software displayed the muon hits, the number of muon decays, as well as the muon decay rate. So as the muons pass through the scintillation pattern, this creates photons, which of course are signals of light. And these photons go through the photomultiplier tube, which then generates an electron, which is then detected by a data acquisition module. So here's an image of our setup. So from left to right, we have the detector column and the data acquisition module. Then we have the oscilloscope, which of course displays the analog hits and the digital pulse. And then we have the laptop, which is fed the data. So here we have a closer look at the scintillator, which will be inside of our detector. And on top of the scintillator will be the photomultiplier tube. So the scintillator has a surface area of 765.76 centimeters squared. So in terms of actually measuring the muon lifetime, once these muons slow to a stop as they enter our detector, they of course will decay into an electron, as mentioned previously. And these decayed electrons are about 207 times smaller than the muon's mass. Thus, they tend to be very energetic and produce a scintillator light along its pathway. So the excited scintillator will then, of course, emit a light, which is then detected by the photomultiplier tube. So this produces a logic signal and then triggers a timing clock. And this timing clock, which of course has successive distributions of time intervals, is what allows us to measure the muon lifetime. So here we have a closer look at the data acquisition module and the top of the detector column. So the photomultiplier tube was set at a high voltage of 1,200 volts. And for the discriminator, we set this to 220 millivolts. So the reason why we set the discriminator to this threshold, as well as the photomultiplier tube, was to allow us to amplify as much signal as possible while keeping the amount of background noise as low as possible. So here's a closer look at our oscilloscope. So in green, we have the analog hits, and in blue, we have the digital pulse. And here's that in comparison with multiple hits. So here we have our first run, and we did a total of 4 runs. So on the left, you can see the number of muons that have been hit, the muons that have been decayed, as well as the muon lifetime in the upper right-hand corner. And here's the comparison of the second run, the third run, and the fourth run. And as you can notice, the curves all follow a similar path of an exponential decay, which is what we expect. And here we have a table which displays all of our recorded data. And in the last row, we have a total of all of our measurements. And from here, we can see our mean muon flux is 0.6 muons per minute per centimeter squared. Our mean muon lifetime was 2.179 plus or minus 0.067 microseconds. For data comparison purposes, we decided to compare our data to SLAC's, their cosmic ray muon detector's data from 2008. And we did this because Palo Alto, which is where SLAC is located, and Louisville have similar latitudes with only a 1 degree difference. It is important to note that the elevation is different, but with only 62 meters, this of course will not result in a difference in our muon flux. So when comparing results, we found that our measured muon flux of 0.6 muons per minute per centimeter squared was consistent with SLAC's, which was also 0.6 muons per minute per centimeter squared. So this was a very good match. Additionally, the measured muon lifetime that we found was within 0.8% that of the particle data group value, which was very impressive. And additionally, as mentioned previously, we can determine the various properties of weak interaction, including the Fermi coupling constant. And this, of course, is what measures the strength of the weak force. So using this formula provided here, we used our measured muon lifetime, and we found a value that is within 0.19% of the PG value. So this, again, is a very good match. We can also determine the W boson mass. So using the standard model formula, we can use our calculator for mean coupling constant value, and we get a value that is within 3.5% that of the LHC's W boson mass measurement. Additionally, we can also determine the Z boson mass measurement. So again, using our W boson mass calculation, we get a value that is within 3% that of the PDG's Z boson mass. So this is also a good match. Additionally, we can also determine the weak coupling constant as well as the strength of the weak interaction. So using our W boson mass calculation, we get that our value for the weak coupling constant is within 3% that of the PDG value. And for the strength of the weak interaction, we of course get a value that is within 0.9%. So this is also a very impressive match. And additionally, we can determine the Higgs expectation value of the Higgs field as well as the Higgs mass. So the Higgs vacuum expectation value is of course what breaks the electroweak symmetry, and this is what makes the W and Z boson so massive. So using this formula, we found that our value was within 0.05% that of standard model, which is extremely remarkable. And additionally, for our Higgs mass, we get a value of 125.1 HeV, while the LHC's Higgs mass is 125.25 plus or minus 0.17 GeV. So this is also a really remarkable match. So here's a table which of course displays our measured and determined values in comparison with the measured and determined values of these accelerated experiments. And in the right, we have the percent differences of our results and the PDG values. And so what you'll notice is the percentages are quite consistent. However, you will notice that for the W and Z boson masses, they are within 3%. But when looking at our error bars, they are consistent with the PDG value. And of course, the best for knowledge, we have not seen any work which has published our data, so we do plan on publishing our work. So based on our results, we can conclude that the caustic ray muon data can successfully determine the properties of the weak force, and this is comparable to the results obtained by high energy particle accelerators, which is quite remarkable. And our data is comparable to that of the PDG values, and of course it is consistent with standard models of particle physics. And in case anyone was curious, based on our measured muon flux of 0.6 muons per minute per centimeter squared, on average, about 5.4 trillion muons are hitting you per year, and about 500 trillion muons are hitting you during your lifetime, assuming you live for 90 years old. Thank you. Are there any questions? Yes, I see a hand.
Oh, okay, there we go.
Okay, can you hear me all right?
Yes.
So I was really impressed to see the quality of work you were getting out of this. I'm working with cosmic rays as well, but looking at just at the fluxes and at the astronomical side. So I was curious then, what is the typical count rate that you're getting with your setup? I see you had 0.6 muons per minute per square centimeter, but what's the, I don't know, your collecting area, what's the count rate you tend to get?
That's a great question. I actually do not know the answer at the top of my head, but I can refer to my mentor who is here and he can provide an answer.
Yes, so if you look at one of the slides, if you come here, if you go to the data in the software slide, all the way back, here, this one here. So your question is your count rate, a number of, is it, you mean the muon rate or decay, or even decay rate, or? I was wondering if you could repeat the question.
Oh, yes. What is the typical count rate that you're detecting?
So in a matter of 24 in matter of 1 hour, sorry, 1 day, we're getting about 679 million muons through a detector. Is that
279 muons per
79
day?
million muons over a 24-hour life time frame?
Okay. So I'm curious if you are, because we're going into near the solar maximum now,
Right.
and the solar activity is anti-correlated with the cosmic ray muon rate. Are you
Correct.
seeing any decrease over long periods with this yet?
We haven't done a continuous study, but we could. We did 4 rounds for 24 hours, but we could continue this and see if there's a change. Yeah, that's a good experiment that you mentioned.
Yeah. We're doing the same thing upstairs right now, but just with using a pair of Geiger counters set up with a coincidence detector in order to select for near the zenith so that we're getting cosmic ray muons and not simply radiation from the concrete walls. Do you have any way of distinguishing local sources of radiation, like again from concrete?
Yeah, we're the room that we have the detector, it is I don't believe there is much concrete except the walls. So it's just next to the window in a dark room. So we don't have any way to, so to answer your question, we don't have much concrete at all. Yeah.
Okay, thanks.
Yeah, then any questions online? No? Well, then let's thank Samia again.
Thank you.
Okay, this closes the talk part of today, and we will go over to the member meeting. So I will stop the recording, going back to my thing, and I give it over to Alan as the president.
Well, good morning or afternoon, whatever it is there. Again, sorry I couldn't make it. The primary things we need to discuss, I guess, in the membership meeting to start with is next year's meeting. I've heard that Berea is